What's the simplest question you can ask about a number? Not what it equals, not what you can do with it. Just, can it be broken into smaller pieces? Can it be built from something else? Or is it just irreducible? Just itself? That's it. That's where we're starting tonight. And from that one tiny question, smaller than a grain of sand, simpler than anything you studied in school, we're going to follow the entire history of prime numbers, every major discovery, every dramatic story, every mystery that's still unsolved right now. Centuries after, some of the greatest minds in human history tried their best and gave up. All of it. So get comfortable, settle in, pull the covers up if you haven't already. This is going to take a while, and that's kind of the point. Let me start with something so basic it might feel almost embarrassing, but I promise it's worth saying carefully. What actually is a prime number? You probably have a rough memory of this from school. Maybe the word prime brings back a list. 2, 3, 5, 7, 11, 13. You might even remember that 2 is the only even prime, which is one of those facts that feels vaguely important without ever being fully explained. But here's the thing, and this is what I want you to actually feel. Remember, prime numbers are not just a category that mathematicians invented to organize things neatly. They're something more fundamental than that. Think about the number 12. You can break 12 apart. 12 equals 4 times 3. But you don't have to stop there. That 4 can itself be broken down. 4 equals 2 times 2. And now you're stuck. 2 can't be broken down. 3 can't be broken down. 2 and 3 are the pieces that don't have pieces. You've hit the bottom. And here's what's genuinely remarkable about this. Every single whole number, every one of them, without exception, can be broken down in the same way. You keep breaking and breaking until you can't break anymore. And what you're always left with at the very bottom of the pile are primes, just primes, nothing else. Think about that like the periodic table for a moment. Every molecule you've ever encountered water, glass, the air in this room right now is made from combinations of chemical elements, iron and oxygen, carbon and hydrogen. The elements are the irreducible units. You can't simplify a gold atom into something smaller and still have gold. In exactly the same way, every number you've ever seen is built from primes. The number 30 is 2 times 3 times 5. The number 100 is 2 times 2 times 5 times 5. The number 1,386 is 2 times 693. And if you keep going, you eventually hit primes all the way down. This idea has a proper name, the fundamental theorem of arithmetic, which sounds very grand and official, but what it really says is just primes are the atoms of arithmetic, and every whole number is a molecule made from those atoms. I love this framing, honestly, because it takes something that sounds like a dry classification exercise and turns it into a statement about the deep structure of reality. Numbers aren't just a list. They have an architecture, and primes are its foundation. So where does this story actually begin? We need to travel about 2,300 years back, to a city that was, at the time, the intellectual capital of the known world, Alexandria, Egypt. Around 300 years before the Common Era, the Great Library is in its prime, so to speak. Ships come and go in the harbor. Scholars from Greece, Persia, Babylon, and India mingle in its corridors. And working there, somewhere in that extraordinary place, is a mathematician named Euclid. We don't know much about Euclid as a person. That's one of the quiet frustrations of ancient history. The men who changed everything are often the least documented. We don't know when he was born. Exactly. We don't have letters, portraits, or personal accounts. What we have is his work, specifically a book called The Elements, which is arguably the most successful textbook in the history of human civilization. It was used as the primary geometry textbook in schools and universities for over 2,000 years. Think about that for a moment. A book written around 300 years before the Common Era was still being handed to students in the 1800s. Euclid's geometry was so complete, so carefully constructed, that there was essentially nothing to improve. The Elements covers an enormous amount of mathematics, but buried inside it, in Book 9, there is one result about prime numbers that I want to tell you about carefully, because it is, in my opinion, one of the most beautiful things in all of mathematics. And it's only 4 lines long. Euclid wanted to answer a very natural question. Do prime numbers ever run out? You've got 2, 3, 5, 7, 11. They keep appearing as you count higher. But is there a biggest prime? Is there some number after which you'll never find another one? Now here's the remarkable thing. Euclid answered this question definitively, permanently, completely, in 4 lines of argument that a clever teenager could follow. Here's how the proof works, and I'll walk you through it slowly because the elegance of it is genuinely worth savoring. Just suppose that there's a finite list of all the primes. Maybe there are 5 of them, maybe 5 million, but some final list. Call them prime 1, prime 2, prime 3, all the way to the last one. Euclid says, take all of those primes and multiply them together, every single one, and then add 1 to the result. You now have a new number. What is this number divisible by? Well, divide it by prime 1. You get a remainder of 1 because you multiplied all the primes together and added 1. So dividing by any prime on your list leaves a remainder of exactly 1. Same with prime 2. Same with every prime on your list. None of them divide evenly into this new number. So either this new number is itself a prime 1 that wasn't on your list, or it has prime factors that aren't on your list. Either way, your list was incomplete. Your list was always going to be incomplete. You cannot have a finite list of all the primes. They go on forever. Just let that actually land for a second. Not the proof, the age of it. From a few simple observations about remainders and multiplication, a man working in Alexandria 2,300 years ago settled this question permanently. There is no biggest prime. They go on and on as far as counting goes forever. And here's the thing that makes this proof so remarkable. It's not just that it works, it's that nobody in 2,300 years has found a better way to say it. Euclid's proof is 4 lines. It uses no advanced machinery. A clever teenager could follow it, and it settles the question permanently. That almost never happens in mathematics. Most results get refined, extended, given cleaner proofs by later generations. Euclid's proof of infinite primes just sits there, pristine and untouched, like it was carved from something harder than stone. I find that genuinely moving every time I think about it. The idea that the oldest known proof of a fact about prime numbers is also the best proof, that 2,300 years of mathematical progress haven't produced a single improvement on 4 lines written in ancient Alexandria. Now, around the same era, in the same intellectual world, there was another person we should meet. His name was Eratosthenes, and he was born around 276 years before the Common Era in a city called Cyrene in what is now Libya. He eventually made his way to Alexandria as well, because the great library attracted everyone of consequence, and he became its chief librarian. Eratosthenes was one of those extraordinary generalists that the ancient world occasionally produced. A mathematician, a geographer, a poet, and an astronomer all at once. This guy calculated the circumference of the earth with remarkable accuracy using nothing but a stick, the angle of a shadow, and some careful reasoning. Just that one detail alone makes me want to stop and spend an hour telling you his whole life story. But what we're here for tonight is his sieve. Eratosthenes had a beautiful, tactile idea for finding prime numbers. Imagine you have a very long hallway with numbered doors, stretching as far as you can see. Door 2, door 3, door 4. Every whole number going on and on into the distance. You want to mark all the prime doors? Here's what you do. Start at door 2. 2 is prime. Mark it open. Now walk down the hallway and close every second door. Door 4, door 6, door 8, door 10. Every multiple of 2 gets closed. None of those can be prime because they're all divisible by 2. Come back, move to door 3. 3 is still open. So 3 is prime, mark it. Now walk through and close every third door from here. Door 9, door 12, door 15. Every multiple of 3 that hasn't already been closed. Move to door 5, still open, prime, close its multiples, then 7, then 11. You keep moving, and every door you reach that's still open is prime, because you've already eliminated everything that could divide into it. The prime doors just stand there, open, while everything else has been shut. Eratosthenes called this a sieve, and that's exactly what it feels like. You're sifting the whole numbers through a series of filters, and the primes are what won't pass through any of them. They're what remains, what the sieve reveals. If you actually run it and look at the pattern of what's left open, is something quietly strange. The primes at the beginning crowd together. 4, 3, 5, 7, practically touching, then 11, 13, still close, then 17, 19, but keep going further and the gaps begin to widen, then widen more. Then, occasionally, two primes appear side by side, again separated by just two, like 11 and 13, or 17 and 19, and mathematicians call these twin primes. They feel like a pair of old friends you keep running into unexpectedly in a crowd that's getting larger and more spread out. And then there are the silences, long stretches of composite numbers, numbers with factors, numbers that can be broken down with no prime anywhere in sight. A gap of 14 numbers with nothing, a gap of 34 numbers with nothing. There are what you might call prime deserts, long regions of the number line where the primes simply disappear. And you walk and find nothing, and then suddenly one appears again. Alone, out of nowhere, this irregular rhythm clusters and then deserts, twins, and then long silences was deeply unsettling to anyone who thought carefully about it, because it looked like primes should be following some rule. It looked like there was a pattern hiding just beneath the surface, something you could almost grasp. And yet every time a mathematician tried to write that pattern down, it dissolved. The primes kept their secret. Other civilizations were circling around these same ideas from different directions during this period. In China, mathematicians working around this era were developing sophisticated tools for understanding divisibility techniques. We now group under the name the Chinese remainder theorem, which describes how to combine information about remainders when dividing by different numbers. The theorem is, at its heart, a statement about how primes interact with each other, how they are essentially independent of one another, how knowing something about a number modulo 1 prime tells you nothing about the number modulo a different prime. The Greeks had isolated primes as objects of study. Chinese mathematicians were uncovering the same deep structure from a completely different angle through practical calculation problems rather than abstract proof. In India, ancient texts showed careful attention to questions of divisibility and common factors, the idea of a number being irreducible, unbreakable, was present, expressed differently, approached through different problems, but pointing at the same underlying reality. The fascination with what numbers are made of seems to be something that independent civilizations couldn't help bumping into, each in their own way, in their own time. So by the time we leave the ancient world, somewhere around the 2nd or 3rd century of the Common Era, humanity had accomplished something genuinely remarkable with prime numbers. We knew that they were the building blocks of every whole number that exists. We had a proof, clean and permanent, that they never run out. We had a method, elegant and tactile, for finding them. And we had noticed, with a growing unease that no one quite had words for, that they were behaving in ways that defied any simple description, dense in some places, absent in others, appearing in pairs and then vanishing, obeying no formula anyone could write down. Euclid had answered one question so completely that it will never need to be answered again. But in doing so, he had made another question visible, a question that was somehow harder and stranger, and would prove almost infinitely more difficult to even begin approaching, because knowing that primes go on forever turned out to be the easy part. The hard part, the part that would consume the next 23 centuries of mathematics, was figuring out where they actually show up. And for a long time, nobody made much progress on that question. The knowledge the Greeks had built sat, waiting in manuscripts that were about to take a very long journey. The manuscripts did travel. That's the first thing to understand about what happened next. The knowledge Euclid and his generation built, the definitions and proofs and theorems about primes and the deep structure of numbers, didn't just sit quietly in Alexandria, waiting for someone to find it again. It moved, and the civilization that moved it, preserved it, extended it, and handed it on is one that doesn't get nearly enough credit in most retellings of this story. We're in the Islamic Golden Age now, roughly the 8th century through the 12th, centered in Baghdad and Cairo and Persia. And one of the most important things to understand about this era is what it actually did, because the common framing gets it wrong. The common framing says Islamic scholars preserved the Greek tradition and passed it along to Europe as if they were a relay runner who took the baton, stood still, and waited for someone else. That framing undersells what actually happened by quite a lot. Baghdad in the 9th century was the intellectual center of the world. The Abbasid Caliphate had built something called the House of Wisdom, the Bait al-Hikmah, a palace complex and library and translation bureau and research institute all in one. I genuinely love this institution as a concept because it represents such a deliberate choice, a civilization deciding that systematically gathering human knowledge from everywhere was worth the enormous effort. The translation movement was a systematic, state-funded project to put every major Greek scientific text into Arabic. Euclid's Elements was translated, Archimedes was translated, but it wasn't passive copying. These were scholars who read Euclid and argued with him, found gaps in the arguments, and wrote treatises in response. They were in genuine conversation with the Greek tradition, not just archiving it. And one of those scholars, working in Cairo around the year 1000, quietly worked out something about prime numbers that the Greeks had never found, something that wouldn't be independently rediscovered in Europe for another 700 years. His name was Ibn al-Haytham, born around 965 inches Basra in what is now Iraq. He is, by any honest measure, one of the most extraordinary scientific minds of the medieval world. His 7-volume work on optics, completed around 1011, is sometimes placed alongside Newton's Principia as one of the books that fundamentally changed how humans understand the physical world. He was the first person to correctly describe how light travels from objects to the eye, not the reverse. He described how lenses work. He laid out an early version of the scientific method. He was doing all of this in Cairo, working under the Fatimid Caliphate, and somewhere in the middle of all of it, He noticed something genuinely strange about primes. Here's the theorem. Take any prime number, call it p. Think about all the whole numbers from 1 up to p minus 1. Multiply them all together. Then add 1. The result is always divisible by p perfectly, cleanly, no remainder. If p is 5, 1 times 2 times 3 times 4 is 24. Add 1, 25. Divisible by 5. If p is 7, 1 through 6 multiplied is 720. Add 1, 721. Divide by 7, 103. Exactly. Every time, with every prime. And here's the part that I find genuinely arresting about this. There is no obvious reason this should be true. Multiply all the numbers below a prime together and add 1, and somehow always land on a multiple of that prime. It sounds like a coincidence until you realize it can be proved, that it follows necessarily from how primes interact with multiplication. Al-Haytham found this around the year 1000. The theorem is now called Wilson's theorem, named after a British mathematician who rediscovered it roughly 7 centuries later. Wilson's theorem, not Al-Haytham's. History is, in this as in many other things, a little rough about its attributions. What the theorem really revealed was that prime numbers have hidden internal structure, not just the absence of divisors, which is how we usually define them. They have these precise, almost uncanny relationships with the numbers around them, a fingerprint. And Al-Haytham was one of the first people to catch a glimpse of it. The knowledge moved again over the following centuries. The mathematical tradition built in Baghdad and Cairo and Persia began flowing west through translation centers in Spain and Sicily, through trade routes and borrowed manuscripts, and through specific people who made the crossing themselves. One of the most important was a young man from Pisa. Leonardo of Pisa was born around 1170. His father was a customs official working at a trading post in what is now Algeria, and Leonardo grew up there, learning mathematics from the Arabic-speaking North African merchant world. He absorbed the Hindu-Arabic numeral system the way you absorb a language when you hear it every day. He came back to Pisa and in 1202 published Liber Abaci, the Book of Calculation, which introduced the Hindu-Arabic numerals to a European audience in a form merchants could actually work with. Before Leonardo, who came to be called Fibonacci, Europeans were doing arithmetic in Roman numerals. Try multiplying LX70 by XL live in Roman numerals, and you'll understand immediately why this mattered. Fibonacci changed the symbols with which a civilization did mathematics, and I think that rarely gets the appreciation it deserves. He didn't discover a theorem. He upgraded the instrument with which the whole tradition thought. Everything that followed was built on that foundation. But the mathematics of primes itself was still largely where Al-Haytham and the Greeks had left it. The next genuine forward motion came from a monastery cell in Paris, from a French monk running what was, by any measure, the most important informal correspondence network in 17th century science. Marin Mersenne was born in 1588 inches Maine, in northwestern France. He joined the Order of Minims, settled in a Paris monastery, and remained there for most of his adult life. He wasn't a great original mathematician himself, not by the standards of the company he kept. What Mersenne was, and what he seems to have been uniquely suited to be, was a connector. He wrote letters constantly to everyone of significance in European intellectual life. Descartes, Pascal, Huygens, Galileo, Torricelli. The letters went out in all directions and came back in all directions. Question, results, problems, proofs, challenges. Mersenne read them, summarized them, forwarded the relevant ones, and served as the central switching station through which European scientific thought circulated. I keep coming back to the same image for this. He was the 17th century internet. Every interesting mathematical idea in Europe passed through his monastery cell. He didn't create the network. He was the network. And this particular node had a specific fascination with prime numbers. And with one family of numbers, especially, Mersenne was drawn to numbers of the form 2 raised to a prime power, minus 1, 2 to the power of 2. Minus 1 is 3. Prime 2 to the power of 3. Minus 1 is 7. Also prime 2 to the power of 5. Minus 1 is 31. Prime 2 to the power of 7. Minus 1 is 127. Also prime. These are now called Mersenne primes. And the insight behind them is this. Because of their algebraic structure, there are faster methods for testing them than for arbitrary large numbers. If prime numbers are scattered across the number line, the way rare minerals are scattered through rock, Mersenne's observation was that there are specific geological formations, specific families of numbers, where the search is more efficient. Some of his specific guesses about which exponents gave primes turned out to be wrong, but the idea was right, and it still echoes today. The largest known prime number at almost any point in history has been a Mersenne prime. But now we need to talk about the person who was working at the same time as Mersenne, corresponding with Mersenne, and somehow generating results of a depth and range that make the monk look more specialized. A person who held no academic position, published almost nothing in his lifetime, treated proofs as largely optional, and changed number theory more than almost anyone before Euler. Pierre de Fermat was born in 1600 en Puce, Beaumont-de-Lomagne, a small town in the southwest of France near Toulouse. He trained as a lawyer, became a lawyer, eventually a counselor at the Parliament of Toulouse, perfectly respectable, moderately successful, the kind of career that normally leaves no trace. And in whatever hours remained after the contracts and court cases, he did mathematics not as a dabbler. He thought at a level that genuinely alarmed the professional mathematicians of his day. He wrote to Mersenne, Descartes, Pascal. He sketched theorems in letters and scribbled results in the margins of books, and he almost never included the proofs. He would state the result with complete confidence and provide nothing to justify it except the breezy assurance that the demonstration was, unfortunately, unavailable right now. This drove his contemporaries to a kind of exasperated admiration because the claims kept turning out to be true. Let me tell you about the result that matters most for the story of primes. It's called Fermat's little theorem, and it was the first tool in the history of mathematics specifically designed for testing whether a large number might be prime. Here's how it works. Take any prime p. Pick any whole number a that isn't a multiple of p. Raise a to the power of p minus 1. When you divide that result by p, the remainder is always 1. Always. No exceptions. Concrete example, the prime is 5. The number is 3. 3 to the power of 4 is 81. 81 divided by 5, 16. Remainder 1. The prime is 7. The number is 4. 4 to the power of 6 is 4096. Divided by 7, 585. Remainder 1. Change the prime. Change the number. The remainder is always 1. Here's why that matters. Think of this theorem as a metal detector for primes. If you have a large number and want to test whether it might be prime, you run the check, pick an a, raise it to the power of your candidate minus 1. Divide, check the remainder. If the remainder is not 1, your candidate is definitely not prime. Definitely. The detector didn't beep. Move on. If the remainder is 1, your candidate might be prime. You'd want to run the test with several different values of a, because there are rare composite numbers that can pass the test. But before Fermat, there was no shortcut at all. Testing a large number for primality meant trying to divide it by every smaller number, which becomes impossible as numbers grow. Fermat's little theorem was the first instrument, the first method that could give you real information about a large number without exhausting every possibility. And I think that's easy to slide past without fully appreciating. Alas, so let me say it plainly. Before this theorem, there was essentially no leverage on the problem of large primes. After it, that's not a small thing. Fermat also turned his attention to a different family of numbers, built by taking 2 raised to successive powers of 2 and adding 1. The first several 3, 5, 17, 257, all prime. Fermat looked at this and concluded, with the serene certainty of a man accustomed to being right, that all numbers of this form are prime. He stated this without proof. He apparently didn't feel proof was required. He was wrong. Euler, a few decades after Fermat's death, factored the next number in the sequence and showed it split cleanly into 2 smaller pieces. Fermat's one genuine error in number theory. Now, here's what makes Fermat genuinely maddening. And this is the part I find almost impossible not to love. He was wrong about exactly one thing. The theorems he stated without proof. The results he scattered through his letters and marginal notes turned out one by one over the next 3 centuries to be correct. Mathematicians came back to his writings long after his death and verified them. Fermat had been right again and again. The intuition of the part-time lawyer working by candlelight after court in Toulouse was just, accurate, in a way that defied easy explanation, which makes the most famous thing he ever wrote all the more extraordinary. In a copy of the ancient Greek text Arithmetica by Diophantus, Fermat came across a problem about expressing numbers as sums of two squares. 5 squared equals 3 squared plus 4 squared. Fermat read this and wrote in the margin, "It is impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general any power higher than the second into two similar powers." And then I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. He never wrote the proof anywhere else. No letter, no papier. After his death in 1665, his son found the note and published it, and mathematicians read it. And the next 358 years of number theory includes a substantial chapter of people trying to verify what a dead lawyer had claimed to have proved on some ordinary afternoon. Euler proved it for the case of cubes. Sophie Germain made real progress in the 1800s. The problem consumed careers. It became the most famous unsolved question in mathematics until 1994, when Andrew Wiles published a proof of over 150 pages using mathematical machinery that hadn't existed in Fermat's time. The theorem was true. Fermat had been right. He almost certainly didn't have the proof he claimed. The consensus is that he had an argument that seemed to work in the moment and would have collapsed if he'd written it out fully. But nobody knows for certain. Nobody will ever know. And I think what this tells you about Fermat is something genuinely strange about mathematical intuition. He could see into the structure of numbers in a way his contemporaries couldn't follow. Not because he was working harder, he was working part-time, but because his intuition was calibrated to something real. He saw the mathematical landscape and described what was in it, and mostly couldn't be bothered to draw the maps. And the maps took everyone else 3.5 centuries. There's something almost dreamlike about that. When you sit with it, the man who changed number theory was a lawyer. The most consequential things he apparently did for mathematics were reading old books in his off hours and writing notes in their margins. Notes that mathematicians are still working through today. Fermat had cracked open the door to understanding primes, but it would take a blind man in Switzerland to kick it wide open. And that man, Leonhard Euler, was about to take everything Fermat started and push it further than anyone thought possible. Leonhard Euler was born in Basel, Switzerland, in 1707, and he is, by any reasonable measure, the most productive mathematician who has ever lived. Not the most famous, not necessarily the most celebrated, though he's certainly that too. The most productive. By the time he died in 1783, he had filled more than 80 volumes with original mathematics, 80 volumes. The St. Petersburg Academy of Sciences, where he spent much of his career, was still publishing his unpublished papers decades after his death. He had so many results in the pipeline that it took them 47 years to catch up. I want to tell you something about this man before we get to his mathematics, because the biographical fact is too good to rush past. Euler lost the sight in his right eye in his late 20s, most likely from overwork, from staring at mathematical calculations by candlelight for too many hours at a stretch. And here's what you need to know about what he did next. He kept going. He adjusted his methods slightly, complained somewhat in his letters, and continued producing an extraordinary quantity of mathematics. Then, in his late 50s, something more serious happened. A cataract destroyed his remaining vision almost completely. By 1771, Leonhard Euler was essentially blind. He could not see, and he could not stop. He dictated proofs to his sons. He performed enormous calculations in his head, holding hundreds of intermediate steps in memory without writing anything down. He invented a way of doing mathematics that didn't require sight, because the mathematics had become so deeply embedded in his mind that paper was almost beside the point. His productivity, by some accounts, actually increased after going blind. There is something in that story that I find genuinely moving. The idea that Euler's relationship with mathematics was so fundamental to who he was that the loss of sight couldn't interrupt it. He had moved the mathematics inside. But we're here tonight because of what Euler discovered about primes. And this is where things start to get genuinely beautiful. You remember the zeta function, that infinite sum where you take 1, add 1/2, add 1/3, add 1/4, and keep going forever. Euler had already shown that this sum, when you raise the denominators to different powers, gives you startling results. The sum when you raise them to the second power equals pi squared divided by 6. Pi, that thing from circles, showing up inside a sum made entirely of whole numbers. That kind of result makes mathematicians fall in love with mathematics all over again. But Euler then did something even more remarkable. He found a completely different way to write the zeta function, not as a sum over all whole numbers, but as a product over all prime numbers. Let me describe this without the symbols, because the symbols aren't the point. The inside is the point. Imagine you take every prime number, an, b, an, 2, 3, 5, 7, 11, 13, and so on, forever. For each prime, you build a small factor using that prime, and you multiply all those factors together. Euler showed rigorously that this infinite product over all the primes equals exactly the same thing as the infinite sum over all the whole numbers. Two completely different ways of building infinity. The same result. Euler's product formula is like discovering that the DNA of an infinite series is written in prime numbers. Every term in the sum has a prime hiding inside it. The primes are not just scattered objects you can observe from the outside. They are woven into the mathematical fabric itself. And here's what that means, and why it matters so much. It means the information about prime numbers is somehow encoded inside the sum over all whole numbers. The zeta function holds the primes inside it. The way a pattern of grooves on a vinyl record holds an entire symphony. The zeta function is the record. The primes are the song. Just think about that for a second. Euler went even further. He used this product formula to prove something that has stayed with me since the first time I properly understood it. He showed that if you add up 1/2 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11, and keep going, taking the reciprocal of every prime. This sum is infinite. It doesn't converge. It keeps growing without bound. Forever, you might think. Primes get rarer as you go further out. So surely their reciprocals should eventually add up to something finite. But they don't. Even though primes get rarer, they never get rare enough to stop mattering. The forest might thin out, but it never becomes an empty plain. There's something quietly profound about that result. The primes thin out forever and they stay relevant forever. Their thinning is exactly calibrated, you might say, to keep them present without overwhelming, always there, just barely, always. Euler had found the bridge between the structure of whole numbers and the distribution of primes. He hadn't solved the mystery, not by a long way, but he had given mathematicians a new language to ask the question. The zeta function, this seemingly innocent, infinite sum, was now connected to the deepest patterns in arithmetic, and it would be that connection, that bridge Euler had built, that a young German prodigy would stare at a generation later and begin to sense the shape of something vast. Now let's talk about Carl Friedrich Gauss. Gauss was born in 1777 inches Brunswick, in what is now Germany, and by the time he was a teenager, mathematicians were running out of superlatives. The Prince of Mathematics, they called him eventually, which is not a title handed out casually. There's a story, perhaps apocryphal, that his school teacher once tried to keep a class busy by asking them to add up all the whole numbers from 1 to 100. The teacher expected this to take a while. Gauss reportedly looked at the problem, wrote down the answer almost immediately, and set down his slate. He had noticed instantly that you could pair the first and last numbers, 1 and 100, to get 101, 50 such pairs, 5,050. Done. Whether that exact story is perfectly accurate, the broader picture is clear. Gauss was operating at a level that left his teachers feeling more like observers than instructors. But the moment I want to slow down for tonight, the one that I find genuinely staggering, is not about Gauss, the celebrated adult. It's about Gauss at 15. Picture this. It's 1792. Gauss is a 15-year-old in Brunswick, and he has gotten his hands on a published table of prime numbers, the kind of list serious mathematicians used. He stared at it. He turned it over in his mind the way you turn a strange stone in your hand, looking for the pattern underneath the surface. And he sensed one. He couldn't prove it. He had no formal tools to prove it. But he noticed something in the way primes thinned out as numbers grew larger. The density seemed to change slowly, in a way that felt regular, not predictable in any individual case. You still couldn't say where the next prime would be, but regular in the aggregate, as if the overall shape of the distribution was obeying some quiet, unhurried law. His intuition, formed at 15 by staring at tables, was this: the count of primes up to some large number n is approximately n divided by the natural logarithm of n. Let me say that more slowly, because this is the peak of what we've been building toward. Imagine you pick a very large number, say 1 million. How many prime numbers are there between 1 and 1 million? Gauss guessed the answer is approximately 1 million divided by the natural logarithm of 1 million. The natural logarithm of 1 million is about 13.8. So the estimate gives you roughly 72,500 primes below 1 million. The actual answer is 78,498. Gauss, at 15, with no proof, just by staring at tables and sensing the shape, had found an estimate accurate to within about 8%. He had guessed the prime number theorem, one of the deepest results in all of mathematics. Before he could drive, let that sit for a moment. And here's what this really means. In the most intuitive terms I can give you, the prime number theorem says, I can't tell you where the next prime will be. No one can. The individual primes are wild and irregular, but I can tell you very precisely, on average, how densely primes are packed near any given region of the number line. It's the difference between predicting where a single raindrop will fall and predicting how much rain will fall per square meter during a storm. You cannot do the first. You can do the second. Exactly. The forest has a shape even when the trees are wild. That is one of the most beautiful ideas I know. The unpredictability of individual primes and the deep regularity of their collective distribution existing together in the same object, wild and ordered at once. What Gauss had was an intuition. He didn't have a proof. He refined his estimate over the years but never published it formally, which is, frankly, very Gauss. He had a notable habit of recording his most important discoveries in a private diary and not sharing them, which drove his contemporaries to distraction when they independently discovered the same things and then found out Gauss had been there years earlier. His diary is a source of equal parts admiration and frustration for historians of mathematics. And here's where independent rediscovery shows up again, as it always does in these stories. In Paris, around the same time, a mathematician named Adrien Marie Legendre was thinking about exactly the same question. Legendre was born in 1752 and spent his career at the Paris Academy of Sciences. He was careful, thorough, and he was also, somewhat unfortunately for him, a contemporary of Gauss, which meant he spent a certain portion of his career discovering things that Gauss had already quietly noted somewhere in a diary. In 1798, Legendre published his own version of the prime number theorem conjecture, a slightly different formula, also empirical, also without proof. Two mathematicians in different countries staring at the same scattered data, sensing the same hidden shape. The idea had its own gravity. It was pulling people toward it from multiple directions at once. Now, the next person in this story doesn't always get the attention he deserves. Peter Gustav Lejeune Dirichlet, born in 1805 in the Rhineland, worked for much of his career in Berlin, And he proved something wonderful about primes that I want to describe carefully. Take any arithmetic sequence, any list of numbers with a fixed step. Say you start at 1 and count up by 6. 1, 7, 13, 19, 25, 31, 37. Or start at 3 and count up by 10. 3, 13, 23, 33, 43. Dirichlet asked, how many prime numbers live in sequences like these? The answer he proved in 1837 is this. Take any two numbers that share no common factor. The arithmetic sequence they generate contains infinitely many primes. Infinitely many. Not just a handful, not just a lot. The primes keep appearing in that sequence forever, no matter how far out you go. Pick any two numbers that share no common factor. The sequence they generate is a home to infinitely many primes. There's something deeply satisfying about Dirichlet's theorem. It's a statement about the stubbornness of primes, their refusal to be cornered. You cannot choose a well-formed arithmetic progression and declare it a prime-free zone. They will find their way in. Every valid arithmetic progression contains infinitely many primes. Primes are everywhere you'd expect them to be. The proof Dirichlet used to show this was remarkable in itself. He imported techniques from complex analysis. The mathematics of functions defined on complex numbers to answer a question about whole numbers, using the continuous and complex to illuminate the discrete and whole. It was the kind of cross-domain move that raises eyebrows first and appreciation second. And in St. Petersburg, around the same decades, a Russian mathematician named Pafnuty Chebyshev was doing patient, careful work. Chebyshev was born in 1821 and became one of the great figures of Russian mathematics. He couldn't prove the prime number theorem. Nobody could yet. But he proved something important, just short of it. He showed that the true count of primes never strays too far from Gauss's estimate. He gave precise upper and lower bounds, demonstrating that the ratio of the true count to the estimate stays between two fixed constants, one slightly below 1 and 1 slightly above. He also proved that for any whole number n greater than 1, there is always at least one prime between n and 2 times n. However far out you go on the number line, the primes never become so sparse that you could find a gap of that size without a prime inside it. The scaffolding was going up. The proof wasn't there yet, but its outline was becoming visible by the middle of the 19th century. Then the landscape had changed beyond recognition from what Fermat had left. Euler had built the bridge between the zeta function and the primes. Gauss had sensed the shape of their distribution at 15, with no proof, just intuition and tables. Legendre had independently sensed the same shape. Dirichlet had proved the primes inhabit every well-formed arithmetic progression forever. Chebyshev had tightened the estimates and bounded the gaps. The picture was resolving. The forest was coming into focus. And here's where it gets genuinely strange. The thing that keeps unfolding the longer you sit with it. Euler's product formula doesn't just connect primes to the zeta function in an interesting academic way. It means that understanding the zeta function is understanding the primes completely and fundamentally. The zeta function and the primes are not two separate objects with a useful relationship between them. They are the same question written in two different languages. Every question about how primes are distributed, how many there are up to any given number, where they live, every single one of those questions is, in disguise, a question about where the zeta function equals 0. They're the same question wearing different clothes. And a young German mathematician named Bernhard Riemann was about to look at that question and see something no one had ever seen before, something that would reframe permanently and completely what it meant to ask where the primes are. Gauss had guessed the shape, Euler had built the bridge, but it would take a nervous 32-year-old submitting an 8-page paper he wasn't entirely sure about, to reveal what might be the deepest secret the primes have ever kept. And that paper, just 8 pages, published in 1859, would become the single most important unsolved problem in all of mathematics. Bernhard Riemann was born in 1826 inches, a small village in the far north of Germany. The son of a Lutheran pastor with limited means and a gifted child who tore through mathematics faster than anyone around him could keep up with. As a teenager, he apparently got his hands on Legendre's major textbook on number theory, the same Legendre who had independently guessed the prime number theorem. The book was several hundred dense pages. Riemann reportedly finished it in 6 days, then handed it back and noted that the material was all quite good. He was being, by all evidence, entirely sincere. He eventually made his way to Göttingen, where he studied under Gauss himself. And Gauss, who had a very controlled reputation and did not hand out superlatives carelessly, told colleagues to Wenyu Riemann's early presentations that this young man possessed a gloriously fertile originality. For Gauss, that was essentially a standing ovation. It is 1889. Riemann is 32 years old. He has recently been elected as a corresponding member of the Berlin Academy of Sciences, a significant honor that comes with an obligation. You present the Academy with a new piece of work. Riemann's contribution was 8 pages long. 8 pages. The paper was titled, in translation, On the Number of Primes Less than a Given Magnitude. A title almost defiantly modest, the mathematical equivalent of labeling something that would reshape the next 2 centuries of mathematics as a few notes on counting. What Riemann did in those 8 pages is something no one had done before. He took Euler's zeta function, that infinite sum connecting whole numbers to primes through Euler's remarkable product formula, and extended it into completely new territory. He asked, what happens if, instead of plugging in ordinary real numbers, you plug in complex numbers? Let me explain what a complex number is, because the name sounds forbidding and the concept is actually quite beautiful. You know how, in ordinary arithmetic, you can't take the square root of a negative number. What number, multiplied by itself, gives you -1? Among ordinary numbers, there is no answer. But at some point in the history of mathematics, someone had the audacity to say, let's just invent one, give a name to the square root of -1, call it I, and build a new kind of number around it. A complex number is simply a combination of a regular part and a part involving I, something like 3 plus 2 times I, or 7 minus 4 times I. And here's the thing about these invented numbers. Once you allow them in, mathematics becomes astonishingly more powerful. Functions that are jagged and awkward over ordinary numbers become smooth and well behaved in the complex plane. The universe, somewhat inexplicably, turns out to be deeply at home in this space. Complex numbers describe wave behavior, electrical circuits, quantum mechanics. They were invented out of pure stubbornness and turned out to be the actual language of physics. I find this genuinely delightful every time I think about it, that the same move mathematicians made to avoid saying square roots of negative numbers don't exist ended up being the mathematical vocabulary of the universe. Riemann stepped into this space with the zeta function and found something extraordinary waiting there. To extend the zeta function into the complex plane, he used a technique called analytic continuation. Essentially, find the unique, smooth, consistent extension of a function beyond the region where its original definition applies. The way you might extend a road that disappears into fog by asking what direction it was heading and trusting that direction to continue. Riemann extended the zeta function this way, and he discovered a new landscape on the other side. In this extended landscape, the zeta function has zeros, places where it equals zero, the way a curve dips to touch the horizontal axis. Some of these zeros are easy to understand. They sit at the negative, even integers, -2, -4, -6, and so on. Mathematicians call them the trivial zeros because they arise in a fairly mechanical way from the structure of the function. Expected, did, unexciting. The other zeros are not tidy at all. There are infinitely many zeros scattered through a vertical strip of the complex plane, where the real part of the input sits between 0 and 1. These are the non-trivial zeros, and they're the ones connected to the primes. And here is what Riemann noticed. Every single non-trivial zero he could locate sat on the same line, one specific vertical line, the line where the real part is exactly 1/2, not approximately 1/2, exactly 1/2. He could not prove this was always true, he said, so he noted the observation, said it seemed very likely to hold in general, and moved on. He had other things to cover in 8 pages, but it became the main event. The Riemann hypothesis. All non-trivial zeros of the zeta function lie on the critical line, where the real part equals 1/2. 11 words, roughly, first written in 1859, still unproven. One of the Clay Mathematics Institute's Millennium Prize problems, carrying a reward of $1 million, 165 years and counting. Now, I want to explain why this matters for primes in the most concrete possible way, because this is the connection that earns the hypothesis its reputation. Think back to Gauss's insight at 15 that the count of primes up to any large number is approximately that number divided by its natural logarithm. That's the smooth estimate. But the actual count of primes isn't smooth. It jumps whenever a new prime appears, and it deviates from the smooth estimate in a complex oscillating way. What Riemann showed is that this oscillation is not random noise. It is a superposition of precise waves, one wave for each non-trivial zero, and the position of each zero determines the exact shape and amplitude of its corresponding wave. The zeros are the musical notes. The distribution of primes is the symphony they compose. If all zeros sit exactly on the critical line, the waves stay controlled. The actual prime count never strays far from Gauss's estimate, and primes are distributed as regularly, as predictably in a statistical sense, as they could possibly be while still being what they are. If even one zero sits off the line somewhere out there in the complex plane, beyond any computation, the waves stop canceling. The errors in our prime estimates grow without bound. Everything built on the assumption that Riemann was right becomes suspect. And this, I think, is what the Riemann hypothesis really means at a philosophical level. It's saying that the primes are wearing the deepest disguise available to them. They look random. Each prime is determined by pure arithmetic, no coin flips, no randomness, but they're hiding their structure as thoroughly as any deterministic sequence can. They're pretending to be random as hard as they possibly can, and the hypothesis, if true, says they're doing it perfectly, that there's no hidden layer beneath the apparent chaos that would make them more predictable than they already appear. The primes are as wild as they're allowed to be, and no wilder. There's something genuinely haunting about that. Now here is where the vertigo really arrives. Mathematicians have checked the Riemann hypothesis computationally, verifying each non-trivial zero. As of the early 21st century, the first 10 trillion non-trivial zeros have been confirmed, every single one, on the critical line, exactly where Riemann said. 10 trillion confirmation, and mathematicians will tell you, without drama, that this proves nothing. I love this about mathematics. Genuinely, that the standards of proof are so uncompromising that 10 trillion confirming examples are filed under suggestive but inconclusive. It's a discipline that refuses to be impressed by scale, because in mathematics, 10 trillion examples are not a proof. There are conjectures in number theory where a pattern holds for billions of consecutive cases and then fails, where the counterexample only appears at numbers of astronomical scale, far beyond any direct search. Scale is not truth. Scale is circumstantial evidence. The Riemann hypothesis has the most extraordinary circumstantial evidence in all of mathematics, and it has no proof. Let me tell you briefly about 1896, because it's both a triumph and a reminder of how far we still have to go. Jacques Hadamard, born in 1865, Versailles, was one of the dominant French mathematicians of the late 19th century. He would live to be 97, which gave him a very long time to watch mathematics develop and an equally long time to watch the Riemann hypothesis remain open. Charles Jean de la Vallée-Poussin, born in 1866, Louvain, spent his career in Belgium and was equally long-lived at 96. The two men barely overlapped in age, but they arrived independently at the same result in the same year. They proved the prime number theorem. Gauss's intuition, formed at 15 from staring at tables of primes, that the density of primes near any large number follows a smooth logarithmic pattern, was exactly right, rigorously, definitively, provably right. Both men reached for Euler's bridge, the zeta function, Riemann's extended version, and used the behavior of the zeta function to establish rigorously that the smooth estimate is correct. The same move Dirichlet had pioneered decades earlier, using the continuous and complex to illuminate the discrete and whole. But here's what the proof of the prime number theorem doesn't give you. It establishes the coarse shape of the distribution, the overall logarithmic density. It doesn't tell you how precisely the actual count tracks the estimate at any given point. For that, you need the zeros to cooperate. For that, you need the Riemann hypothesis. The prime number theorem is the map of the continent. The Riemann hypothesis is the claim about how accurately the roads are drawn. Now I want to go back to Riemann himself, because there's something in the end of his story I can't get past. By his late 30s, his tuberculosis had become serious. In the summer of 1866, he traveled to northern Italy, to a small village on the shore of Lake Maggiore, hoping the climate might help. He was 39 years old. He died there on July 20th, 1866, reportedly sitting outside, still working until near the very end, 39. And then his housekeeper did what any conscientious person does when clearing out the study of someone who has just died. She sorted through his papers. She burned what looked like rough drafts, loose sheets, unorganized notes, fragments of calculation he hadn't had a chance to assemble into finished work. She was not a mathematician. She had no way of knowing that a page covered in symbols might be worth more than everything else in the room. We will never know what she burned. The Riemann hypothesis itself appears in the 1859 paper almost as an aside, a conjecture offered with minimal explicit justification. Historians have always suspected that the deeper reasons for believing it, the fuller picture of why it should be true, lived in the notes he never published. In the papers that burned on that lake shore, there is a particular quality to that silence, not the silence of a finished argument, the silence of a thought cut off before it was finished. And here's the part of this story that keeps not just mathematicians, but everyone who learns it genuinely unsettled. In the 1950s and beyond, physicists studying the energy spectra of heavy atomic nuclei, uranium, thorium, the massive atoms at the far end of the periodic table, began noticing something peculiar. The gaps between consecutive energy levels in these nuclei followed a very specific statistical distribution. And when mathematicians ran the same analysis on the gaps between consecutive non-trivial zeros of the zeta function, they found the same distribution, not similar, not roughly the same, the same. The primes are not just talking to number theory, they're talking to physics. There's a conjecture called the Hilbert-Polya conjecture that the non-trivial zeros are secretly the energy levels of some undiscovered quantum system. that somewhere there is a physical object whose quantum mechanics would explain exactly where Riemann zeros sit. Nobody has found this object. Nobody has explained why the connection exists. The primes are whispering to quantum physics through a channel we can hear and cannot trace. And I've sat with this fact a long time, and I still don't fully know what to do with it. It's the kind of thing that suggests the primes aren't just an interesting feature of arithmetic. They might be built into the deep structure of physical reality in a way we haven't begun to understand. And so here we are, 165 years after 8 pages, 10 trillion zeros checked, all cooperating, hundreds of theorems in number theory, random matrix theory, cryptography, and physics, all proven conditionally. On the assumption that Riemann was right, the building stands, vast and functional. The foundation has never been formally verified. Think of it this way. Imagine a building 100 stories tall, standing and in full use for over a century, and someone informs you, we never actually confirmed that the foundation is solid. We designed it from plans left by an engineer who died at 39 before he could write up his notes, and no one has checked independently since. The building is real. It works, but we don't know for certain what it rests on. That is the Riemann hypothesis and modern number theory. If it were disproved tomorrow, an enormous portion of mathematics would need to be rebuilt from the foundation up, not destroyed, rebuilt. Theorems would revert to conjectures, results about prime distribution, the behavior of the zeta function, the foundations of analytic number theory. All of it would need re-examination. If it were proved, we would finally confirm what Riemann had already sensed in 1859, that the primes are as orderly as they can possibly be, that beneath the wild, apparent randomness, the arithmetic universe is tidy in the deepest sense, that the chaos is a perfect disguise, not actual chaos. I don't know which outcome, proof or disproof, would be more beautiful. A proof would give us the clean answer, the confirmation that the universe of arithmetic is exactly as ordered as it appears. A disproof would overturn a century and a half of assumptions and tell us the primes are even stranger than we thought. Either way, we would know something profound. Either way, the story would deepen. The grandest open question in all of mathematics. It belongs to a 32-year-old who handed in 8 pages and then died at 39, and whose housekeeper burned the rest. The story of the primes doesn't close neatly. It extends outward forever, like the sequence itself, always promising another prime just ahead, always delivering and never quite finishing. But here's what might be the strangest chapter of this whole story. While the greatest mathematical minds across a century and a half devoted themselves to cracking the theoretical code of the primes, it turned out that primes had a completely different destiny waiting for them, one that would make them the invisible guardians of every secret you've ever sent over the internet. Because in the late 20th century, someone figured out that the thing that makes primes so hard to predict is exactly what makes them perfect for keeping secrets. For most of the history that we've been walking through tonight, prime numbers were considered the purest of pure mathematics. No engineer needed them, no merchant counted them, no general deployed them. Euclid proved there were infinitely many of them, and then moved on to other problems. Gauss stared at them obsessively as a teenager and spent decades trying to understand their distribution. Not because understanding their distribution would help anyone do anything, but because mathematics is the thing you do when you want to know. Riemann extended the zeta function into the complex plane and found those extraordinary zeros lined up on the critical line. And he wasn't doing it to solve a practical problem. He was doing it because the relationship between primes and that infinite sum was too beautiful and too strange not to follow wherever it led. This is a tradition in mathematics that sometimes baffles people who think about mathematics in terms of usefulness. What are you going to do with this? And the honest answer from Euclid through Riemann was basically nothing, nothing useful. It's just true and interesting, and the truth is worth following on its own terms. And then, in 1977, that entire story turned inside out. Let me tell you about three people sitting together at MIT in the mid 1970s. Ron Rivest was born in 1,947 inches, Schenectady, New York, a computer scientist who had been thinking hard about a problem that seemed almost philosophical. Is it possible to build a lock that anyone can close, but only one person can open? Adi Shamir was born in 1,952 inches, Tel Aviv, a mathematician and computer scientist who had a reputation for coming up with elegant ideas in unusual ways, often quickly, often in the form of sudden, sharp insights rather than slow, sustained effort. Leonard Adelman was born in 1,945 inches, San Francisco, quieter than the other two, more careful, more prone to playing the role of the one who finds the flaw in a proposed solution. He became famous among his collaborators for being the person who says, "This doesn't quite work yet." The three of them were working on a problem that had been formally posed only the year before, in 1976, by two other cryptographers named Whitfield Diffie and Martin Hellman. Diffie and Hellman had asked, in a landmark paper, whether public key cryptography was possible, whether you could have a system where your encryption key was entirely public, you could shout it from the rooftops, publish it in a newspaper, put it on a billboard, and yet still maintain secrets. Because the decryption key, the thing you actually need to read the message, remained private and could not be derived from the public key by any practical method. I want to stop here for a moment because this concept is genuinely counterintuitive, and I think it deserves to land properly. In all traditional cryptography, secrecy depends on keeping your key secret. You and I agree on a code, and the code only works if nobody else knows what the code is. The weakness of this is obvious. We have to share the key somehow, and sharing the key creates a moment where it can be intercepted. Every spy thriller is about that moment. Diffie and Hellman asked, what if you didn't have to share the secret key? What if there was a mathematical operation where I could give you something entirely public? You could use that to encrypt a message to me, but only I could decrypt it, and even though you did the encrypting, you cannot reverse what you did. Rivest, Shamir, and Edelman found the answer, and the answer was built entirely on prime numbers. Here's the thing that makes it work. There is a deep asymmetry in arithmetic, a one-way street baked into the mathematics itself, and it lives right at the heart of primes. Multiplying two large prime numbers together is easy, genuinely, almost trivially easy. Your computer does it in a tiny fraction of a second. Take a prime number with 500 digits. Take another prime number with 500 digits. Multiply them together. You now have a number with roughly 1,000 digits, and that calculation takes no time at all. Now, reverse the question. Take the 1,000-digit number. Find the two primes that multiplied together to produce it. This is the factoring problem, and it is catastrophically hard. Not difficult in the sense of requiring care and attention. Hard in the sense of we have no efficient method for doing it. And the smartest people in mathematics and computer science have been looking for one for decades and have not found it. For numbers of the size used in modern cryptography, factoring would take longer than the current age of the universe on every computer on Earth running simultaneously. The operation that produced the number takes a millisecond. The operation that reverses it is effectively impossible. That gap, that's the whole thing. It's a bit like building a safe by welding two specific pieces of metal together. Anyone can see the safe. Anyone can touch it, examine it, try to open it. But to actually open it, you need to know exactly where the weld is, which two pieces were joined, and the weld is invisible. You can inspect the total result forever. You cannot recover the components. RSA encryption, named for Rivest, Shamir, and Adelman, and published in 1977, uses this asymmetry directly. The public key is essentially a very large number that is the product of two very large secret primes. The math of the encryption and decryption, which involves some elegant number theory built on a theorem that Fermat worked out in the 17th century, operates such that knowing the product but not the two factors makes decryption computationally impossible. The two secret primes are the private key. Their product is public, and nobody can work backward from the product to find them. Every time you make a purchase online, every time your browser shows that little padlock icon, every time a secure message travels from your phone to another phone, RSA or a close descendant of RSA is doing exactly this calculation. Somewhere in the background, your device has agreed on a very large number that is the product of two very large primes, and is using that shared mathematical structure to protect your information. 2,300 years ago, Euclid proved that primes couldn't be broken apart further. That indestructibility, the very property that made primes the atoms of arithmetic in Euclid's proof, is the lock on your bank account today. I find this genuinely staggering, not in an abstract way, in a very physical way. The theorem Euclid wrote in around 300 BCE in a book about geometry is the mathematical foundation of internet security. No one planned this. No mathematician working in number theory for the next 2,000 years was thinking about encrypted transactions. The mathematics was just quietly true, and eventually the world caught up to what it implied. But here's a piece of this that often gets overlooked. RSA depends not just on large primes being hard to factor from, but on large primes being available to use in the first place. If you want to generate an RSA key, you need to actually find two large prime numbers, numbers with several hundred digits each, which means you need a way to check efficiently whether a given enormous number is prime or not. This is the primality testing problem, and it's less obvious than it sounds. You can't just try dividing the candidate by every smaller number for a 300-digit candidate prime. There are more potential divisors than there are atoms in the observable universe. You need something much cleverer. The most widely used approach is called the Miller-Rabin test, a probabilistic method built on a theorem that Fermat discovered about primes and their behavior in modular arithmetic. Yes, the same Fermat whose little theorem also powers RSA itself. He keeps showing up. Miller-Rabin doesn't prove primality with total certainty. What it does is test whether a number is definitely composite or very probably prime. Run it enough times with different inputs, and the probability that a composite number sneaks through as probably prime becomes smaller than the probability that a cosmic ray strikes your computer and corrupts the result. For practical purposes, that's effectively certainty. But mathematicians are not temperamentally satisfied with effectively certain, and in 2002, something happened that genuinely surprised the theoretical computer science world. Three researchers at the Indian Institute of Technology in Kanpur published a paper with a title so understated it barely hinted at what was inside. The paper was called Primes is in P. The three authors were Manindra Agrawal, a professor, and two of his students, Niraj Kayal and Nitin Saxena, both undergraduates at the time. They had solved a problem that had been open for decades. Is there a method for testing primality that is efficient in the formal theoretical sense, that scales reasonably with the size of the number being tested rather than exploding into impossibility? Two undergraduate students and their professor working in Kanpur, India, solved it. The AKS primality test, named for the three of them, was the first algorithm that could determine whether any number is prime in deterministic polynomial time efficiently, provably, without any element of probabilistic chance. The reaction in the mathematical and computer science communities was, by the accounts I've read, genuinely excited in a way those communities don't often get. This was a hard problem, a long open problem, and the solution came from an unexpected direction, from people the field wasn't primarily looking toward. And while all this elegant theory was developing, there was also something much more chaotic and human happening in parallel. People were hunting for very large primes, not for any practical reason, just because. The Great Internet Mersenne Prime Search GIMPs is a distributed computing project that has been running since 1996. Mersenne primes are primes of a specific form, 2 raised to some power, minus 1. That structure makes them somewhat easier to test than arbitrary large numbers, which is why the record holders tend to be Mersenne primes. The project lets volunteers donate their computer's idle processing time to the search, crunching through candidates while the machine would otherwise be sitting idle. When a volunteer's computer finds a new Mersenne prime, there's a real notification, a real announcement, a genuine small celebration. The largest known prime, as of my knowledge, was found through this project, a Mersenne prime with over 24 million digits. Writing it out in full would take more pages than most books. Its practical utility is essentially zero. Nobody needs a prime that long. But thousands of people donated computing time to find it anyway. And when the discovery was announced, the people who care about prime numbers felt something genuine. That's worth sitting with for a second. The prime number problem that began with Euclid's proof of infinite supply, that runs through Gauss's obsessive teenage tables and Riemann's 8 extraordinary pages, is also a thing that ordinary people with home computers in the 21st century volunteer time to advance. The chain of care goes back 2,500 years. It's unbroken, but the story of primes and cryptography doesn't end quietly. In 1994, a mathematician named Peter Shor, working at Bell Labs in New Jersey, wrote down an algorithm that became one of the most consequential theoretical results in all of computer science. Shor's algorithm, if run on a sufficiently powerful quantum computer, can factor large numbers efficiently, not in astronomical time, in time that is practical. In a world with a sufficiently large quantum computer, RSA breaks. Quantum computing would take a long time to explain properly, and this isn't the moment for that full story. But here's the essential thing. Quantum computers exploit properties of quantum mechanics to perform certain calculations in ways that classical computers fundamentally cannot. They can hold what are called superpositions, states where a calculation effectively explores many possible answers simultaneously and for certain specific problems. This gives them an enormous advantage. Shor's algorithm is designed for exactly the kind of calculation that makes RSA hard. It attacks the prime factoring problem directly, and it scales. A sufficiently powerful quantum computer running Shor's algorithm would not need the age of the universe. It would need a much more manageable amount of time. This is like discovering that water can dissolve the weld in our safe. The safe works perfectly against everything we currently have. But if someone builds the right tool specifically engineered for the one vulnerability in the metal, then the safe is no longer safe. We don't have that tool yet. The quantum computers that exist today can run Shor's algorithm, but only on numbers small enough that a classical computer could factor them trivially anyway. Scaling to the numbers used in real-world cryptography requires a quantum machine of a size that faces enormous engineering obstacles and doesn't currently exist. But the theoretical threat is real, and the people who think about these things professionally have not been waiting. The response is called post-quantum cryptography, and the effort to build it has been underway for over a decade. The idea is to find mathematical problems that are hard for quantum computers in the same way that factoring is hard for classical computers. The leading candidates are built on problems from high-dimensional geometry called lattice problems, structures that live in spaces with thousands of dimensions, where finding a short path is provably difficult in ways that quantum computation can't efficiently attack. We're designing locks for a world where the most powerful key-cutting machine doesn't exist yet, because everyone who pays close attention believes it will eventually. And here's what I keep coming back to. When I trace this whole arc, the reason RSA works is the same reason Euclid's proof works. Primes are fundamental. They cannot be broken apart. They are the atoms of arithmetic, the irreducible units from which all other whole numbers are assembled. The gap between knowing that a number is built from primes and knowing which primes built it, that gap is the most valuable real estate in all of modern technology. Every credit card transaction, every encrypted message, every secure voice call or private file traveling across a network, all of it passes through that gap. That small, unremarkable seeming space between what is easy and what is hard, between multiplication and factoring, between a 2-millisecond calculation and the heat death of the universe. Euclid did not know this was coming. Fermat did not know. Gauss did not know. Riemann, writing his 8 pages in 1859, was thinking about zeros on a critical line in the complex plane, not about the security infrastructure of a global communication network that wouldn't exist for another century. And yet every piece of what we've described flows from the same source. The deep, strange, irreducible nature of prime numbers. There's something I find deeply satisfying about that. The useless becomes essential. The abstract becomes the invisible architecture underneath everything. The mathematics that was done purely for its own sake, because mathematicians couldn't stop caring about it, turned out to be the foundation that the modern world stands on. So primes protect your secrets and underpin your digital life. But the deepest questions about them, the ones mathematicians have been chasing for centuries, are still completely open. And in 2013, a quiet lecturer at the University of New Hampshire, who had once worked at a Subway restaurant, cracked open a door that had been shut for 1,000 years. Because the story of prime numbers is not finished. It's not even close to finished. And the people writing the next chapter are alive right now. There's a particular feeling that comes when you step back from a practical problem and return to the pure thing underneath it. We've just spent time in the world of cryptography and quantum computing, the world where primes do things, where their properties get deployed, where their hardness becomes a useful tool. All of that is fascinating, but the primes themselves don't care about any of it. They were always just there, as sitting in the number line, waiting, and there are questions about those primes, simple, clean, fundamental questions that have been waiting just as long, that nobody has answered yet. That might be the hardest problems in all of mathematics. Let's talk about 2 of them. The first one you could explain to a 10-year-old in 30 seconds. Look at the primes: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and keep going. Notice anything? Some of them come in pairs, 3 and 5, 11 and 13, 17 and 19, 29 and 31. These are called twin primes, pairs of primes that are exactly 2 apart from each other, with just one even number sitting between them. As you go further along the number line, they keep appearing. They get rarer as numbers get larger, but they keep showing up. The question is, do they ever stop? Are there infinitely many twin primes, all the way out to infinity? Or is there some enormous pair so large nobody has found it yet that is the very last twin prime, beyond which all consecutive primes are separated by larger gaps forever? Nobody knows. The twin prime conjecture says the pairs go on forever. It has been suspected since antiquity. It has been checked for a long time. Twin primes have been found out to numbers with hundreds of digits, and they keep appearing. But suspecting something and proving it are, as we've established, very different things. The second question was asked in 1742 in a letter. Christian Goldbach was born in 1690 Zoll, Königsberg, a mathematician and diplomat who moved through educated European society doing mathematics as part of a broader life of letters. He was corresponding with Euler, which meant his ideas were going to one of the most powerful mathematical minds alive. And in that letter, he posed a simple observation as a question. Every even number greater than 2 that he had checked seemed to be the sum of 2 primes. 4 equals 2 plus 2. 6 equals 3 plus 3. 8 equals 3 plus 5. 10 equals 3 plus 7, and so on. He asked Euler if he thought this was always true. Euler thought it probably was, though he couldn't prove it. That exchange became Goldbach's conjecture. Every even integer greater than 2 is the sum of 2 primes. It has been checked up to 4 times 10 to the 18th, 4 followed by 18 zeros. Every even number up to that immense bound is indeed the sum of 2 primes. Not one counter example, and no proof. There's something genuinely maddening about both of these. They're not obscure questions about structures that only specialists encounter. They're questions about the simplest possible arithmetic addition, subtraction, jumps between numbers on a line. A child can understand them instantly, and professional mathematicians, with all the machinery of modern number theory, cannot reach them. Part of why is something deep and somewhat beautiful. Primes are defined by multiplication. The whole structure of primality is multiplicative. But Goldbach and the twin prime conjecture are questions about addition, about sums and differences and gaps. The relationship between how numbers behave under addition versus multiplication is one of the deepest and most poorly understood territories in all of mathematics. The two operations are entangled in ways that are profoundly difficult to reason about. And that is where so much of the hardness lives. And then, in the spring of 2013, something shifted. Yi Tangjiang was 58 years old. He had been born in Shanghai in 1955, and his early mathematical career had been interrupted by the Cultural Revolution. He spent years doing manual labor before eventually getting to university. Then eventually, making his way to the United States for graduate school. He finished his PhD in 1991 and then, for a period of years, could not find an academic job. He worked as an accountant, he worked odd jobs, he worked at a Subway sandwich restaurant. Not a particularly glamorous chapter for someone who would later be recognized by the mathematical world as having done something extraordinary. He eventually found a position at the University of New Hampshire, where he taught calculus year after year as a lecturer, not a tenure-track professor. Alexandria. He was not at a famous institution, not in a prominent research group, not publishing regularly. By the measures academic mathematics uses to evaluate its members, he was not on the radar. He was also quietly thinking about prime gaps. The problem he was working on was a precise, weakened version of the twin prime conjecture, not whether primes are infinitely often exactly two apart. He wasn't trying to prove that. He was asking something more modest. Is there any fixed finite bound such that primes are infinitely often within that distance of each other, that no matter how far out along the number line you go, you always eventually find two more primes that are close? This was still a genuinely hard problem. It had been completely open for a long time. In 2013, he submitted a paper to the Annals of Mathematics, one of the most prestigious mathematical journals in the world. The referees reviewed it unusually quickly because the argument was clean and found it correct. Zhang had proved that there are infinitely many pairs of primes within 70 million of each other, not two apart, 70 million, but finitely, fixedly, bounded, infinitely often, forever out along the number line. There are pairs of primes no more than 70 million apart. 70 million sounds like a lot, but in the context of numbers that grow without bound, 70 million is nothing. It's a concrete finite distance, and the proof was the first crack in a door that had been shut for centuries. What moves me most about this story is not the mathematics, it's the shape of the life. A man who spent years outside academia, who worked in a sandwich shop, who taught introductory calculus at a regional university, and who then produced, at 58, a result that the entire mathematical world immediately recognized as extraordinary. He didn't invent new tools. He found a way to assemble existing techniques developed by others over decades in a combination nobody had seen before. He had simply been thinking about it carefully and without hurry for a very long time. And then the mathematical community took his 70 million and started running. Within months, a project called Polymath, a collaborative open mathematics effort where anyone could contribute, had taken Zhang's argument and refined it dramatically. The bound dropped from 70 million to millions, then to thousands. Dozens of mathematicians contributed, each trimming the argument a little further. And then a young mathematician named James Maynard, working independently at Oxford, introduced a different technique, entirely more efficient in a key way, and brought the bound down to 600, then to 462, then, with continued refinement, to 246. 246, that is the current state of human knowledge about twin primes. We know that there are infinitely many pairs of primes within 246 of each other. We do not know if there are infinitely many pairs within 2 of each other. But here's the thing that stays with me. Zhang didn't solve the twin prime conjecture. Maynard didn't solve it. The Polymath project, with dozens of the world's best mathematicians working together, couldn't get below 246. That number is where we've been stuck. The gap between 246 and 2 is like standing on a mountain ridge and seeing the summit right there, close enough to feel real, except the last stretch of trail hasn't been built, and nobody knows how to build it. The methods that brought the bound from 70 million down to 246 seem to run out of steam right at that edge. Getting from 246 to 2 requires something new, something we don't have yet. The primes are guarding their secret well. There are other open questions at the frontier alongside these. Are there infinitely many Mersenne primes? Or does that sequence eventually run out? Nobody knows. How large can prime gaps get relative to the size of the primes themselves? There's a conjecture called Cramer's conjecture that gives a precise prediction, unproven. How evenly are primes distributed in short intervals of the number line? These questions all connect at their root to the Riemann hypothesis, to those zeros on the critical line in the complex plane. In a real sense, every open question about how primes scatter is still waiting on what Riemann sensed in 1859 to be resolved. The horizon keeps extending. I want to look back over the whole journey before we let it go. We started with Euclid around 300 BCE, who proved with pure logic that the primes never stop. No instruments, no formulas, just an argument so clean it has survived intact for 2,500 years. We moved through Fermat in the 17th century and Euler in the 18th, and watched Euler build the bridge between infinite sums and the product over primes, the first real connection between analysis and number theory. We watched Gauss, as a teenager, sense the logarithmic pattern in prime density, and saw that teenage intuition become, a century later, a theorem. We spent time with Riemann and his 8 pages, and the hypothesis at the center of mathematics that still stands unproven. We watched primes step out of the pure world and into the architecture of the internet, and we ended here, with Zhang at 58, working quietly, pushing a door open that nobody had been able to move. A single continuous thread of human attention, stretching across 2.5 millennia, pulled along by the same question in different forms. What are the primes? Really? Where do they sit? Is there a pattern beneath the pattern? We still don't fully know. And I've come to think that's not a frustrating answer. The primes are a bit like stars. You can map their density. You can predict roughly how many you'll find in any given stretch of the number line. You can describe their large-scale distribution beautifully and precisely, but you cannot predict exactly where the next one will appear. You cannot say with certainty where the next twin pair will emerge. Each prime sits where it sits because of pure arithmetic necessity, no randomness, no chance. And yet the pattern they collectively form has the texture of something wild, structured wildness, determined chaos. The most orderly possible disorder. We started tonight with a question a child could ask: which numbers can't be broken apart? And we ended up touching cryptography, quantum physics, the nature of proof, and a connection between prime zeros and the energy levels of atomic nuclei that nobody has explained. All of that from 2, 3, 5, 7. What comes next and why? The answer keeps getting richer the longer you look. The deeper you go, the more there is. Euclid could prove they were infinite. Riemann could sense the music they made. Jung could push one boundary quietly after a lifetime of patient thought. And somewhere right now, someone is looking at a piece of this problem that nobody else has thought to look at yet, sitting with the numbers the way Jung sat, the way Gauss sat as a teenager with his tables, and the primes are there, patient, waiting to see what that person finds. The primes are still there. They're scattered across the number line, exactly the way they were when Euclid first proved they'd never stop. 2, 3, 5, 7, 11. The sequence continues in total indifference to whether we've understood it. It doesn't need our attention. It doesn't need our proof. It carries its structure and its mystery outward through every number anyone will ever name, through all the numbers beyond those, without end. You don't have to hold any of this right now. Let it settle somewhere quiet. The open questions will still be open in the morning, patient as they've always been. The primes have been waiting 2,300 years for someone to understand them fully. They can wait a little longer.